Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 4. Multivariate Regression. Multivariate regression is a statistical technique used to model the relationship between multiple independent variables, predictors, and a dependent variable, outcome. The technique is an extension of simple linear regression, which deals with a single independent variable. In multivariate regression, we examine how several variables simultaneously affect a single outcome. Multivariate regression is an essential tool that is used for decision-making and process improvement across different science and engineering disciplines, such as energy efficiency prediction, optimizing the yield of a reaction, modeling economic data, understanding how multiple risk factors affect system integrity, and so on. The least squares regression can be applied to linear and nonlinear regression models, referred to as multivariate regression or multivariate least squares. Linear model is the most common multivariate linear regression model with m independent variables and results in as follows. Here, y is the dependent variable, which is the outcome we are trying to predict or explain. x1 through xm are the independent variables. They are the factors or predictors that are assumed to influence the dependent variable. The relationship between the dependent variable and independent variables is assumed to be linear. This means that the change in the dependent variable is proportional to the change in the independent variables. The objective function, that is, the sum of the squares of the residuals, SSR, for a set of n data becomes, where a0 through am are the model parameters. Basic assumption for the multivariate regression are linearity. There is a linear relationship between the dependent variable and independent variables. Independence. The residuals, errors, are independent of each other. Homoscedasticity. The variance of the residuals is constant across all values of the independent variables. Normality. The residuals should be approximately normally distributed. The objective function is a single equation with m plus 1 unknowns. We derive m plus 1 equations by differentiating e with respect to the model parameters a0 through am and then setting each equation to 0 as follows. The linear system in matrix form can be expressed as follows. Note that the system of linear equations may become ill-conditioned. Make sure to check for ill condition and take necessary precautions when solving it. Nonlinear model. Frequently encountered nonlinear models involving multiple variables have the following power law or exponential forms. These models can be linearized similarly to the univariate models by taking the natural logarithm of both sides of the model, leading to the expressions for power law model and for exponential model. The advantages of multivariate regression are: multivariate regression provides a tool to determine relationships or the relative influence of the predictor variables on the outcome. It allows better prediction capability due to having multiple variables, predictors, i.e., it is not dependent on a single predictor. It provides the capability to identify outliers or anomalies. The disadvantages are: multivariate nonlinear regression can be a bit complicated and may require high-level mathematics and programming techniques. The output of multivariate regression models may be a bit more difficult to interpret. It does not have much scope for small data sets. The results of a series of experiments conducted to determine the compressive strength, Y, of the concrete mix as a function of cement content, X1, and aggregate content, X2, are tabulated below. Assuming that the linear regression model is suitable for modeling compressive strength, determine the model parameters using the least squares method. The linear model leads to the following system of equations expressed in matrix form. For the dataset, the system requires the following sums to obtain the model parameters. To start, we tabulate the original dataset by assigning subscripts. The 3x3 system of equations for the linear regression requires the sum of x1s, x2s, y's, etc. To obtain these quantities, we complete the table as follows. Substituting the numerical values of the sums, we obtain the following matrix equation, whose numerical solution yields the following. Next, we investigate the SSR and SSMD. To do this, we calculate the squares of the mean deviation and the residuals and tabulate them. The column sums give the sums of the squares of the mean deviation and the sum of the squares of the residual. We obtain these quantities as follows. Then the R-squared value is obtained as 0.91952. The best way to determine the goodness of fit for multivariate regression models is to make a PO plot. When the observed and predicted values are fitted to a line, we obtain the slope of 0.91955, corresponding to 42.6 degrees, and the bias of 26.6, which corresponds to just about 8% of the average y. We note that the data points are spread evenly alongside the 45-degree line, which suggests that the model is making random errors. In fact, the best fit line and the 45-degree line agree very well in the validity range of the linear regression. The root mean square error found to be 1.912. When we add the 95% confidence interval to the PO plot, we observe that all data points are within the confidence interval. We conclude this lecture by noting that the linear model is suitable for the problem under consideration and has good predictive potential. That is all for now. See you next time with another topic. Bye.